Okay, we just finished part three on Archimedes' principle, and part four is actually a continuation of Archimedes' principle. Let me dismiss my my image, and we'll continue on. Flotation, the principle of flotation. A floating object displaces a weight of fluid equal to its own weight. Example, a solid iron 1 ton block may displace 1/8 ton of water and sink. The same 1 ton of iron in a bowl shape displaces a greater volume of water. The greater buoyant force allows it to float. So both of these are a ton, but because of the shape, it displaces a lot more water. Oop, it displaces more water so that it floats. Okay, let's see. The reason a person finds it easier to float in salt water compared with fresh water is because the buoyant force on a given volume is greater in salt water than in fresh water. The gravitational force is diminished by salt. Salt water has a lower density than fresh water. A person's volume is reduced more in salt water. Well, you don't know up at this point, unless you've studied it, you don't know that the density of salt water is 1,035 kilograms per cubic meter, whereas fresh water is 1,000 kilograms per cubic meter. Knowing that the density of salt water is greater would lead you to A, the buoyant force on a given volume is greater in salt water than in fresh water. Went too far. But the buoyant force on a given volume is greater in salt water than in fresh water. Salt water is more dense than fresh water. Thus, there's a greater buoyancy force on each cubic centimeter of water displaced. Okay, on a boat ride, the skipper gives you a life preserver filled with lead pellets. When he sees the skeptical look on your face, he says that you'll experience a greater buoyant force as you fall overboard than your friends who wear styrofoam-filled preservers. He is correct about the buoyancy, and you have nothing to fear. B, he is correct about the buoyancy, but you will nevertheless sink. C, he is incorrect about the buoyancy, but you will float anyway. And D, he is completely incorrect. Well, the answer is he is correct about the buoyancy, but because the weight will be greater than what you displace, you will sink. He's correct, but he fails to tell you that you would drown if you fell overboard. Your life preserver would submerge and displace more water than those of your friends who would float on the surface. Although the buoyant force on you will be greater, the net downward force is greater yet because a lead-filled preserver has a much greater weight than a styrofoam-filled preserver. Okay. Now, you place an object in a container that is full to the brim with water and a scale. The object floats, but some water spills out. How does the weight of the object compare with the weight of the water displaced? The weight of the object is greater than the weight of the water displaced. The weight of the object is less than the weight of the water displaced. The weight of the object is equal to the weight displaced. And I'd say it's C. Yes, the weight of the object is greater than the weight of water displaced. This principle is wonderfully illustrated by Scotland's Falkirk wheel. And there's the Falkirk wheel. The Falkirk wheel's two caissons are brimful of water and the same weight, regardless of whether there are boats in them. This makes rotation and lifting almost effortless. Now, I'm going to do a new share, and I'm going to, hopefully it works. I'm going to show you the Falkirk in action. Let's see. Your screen sharing is paused. Resume share. Let me stop share. Let me share the screen and find that again. Because I think it's worth looking at. I mean, it's one thing to just see a picture, but to see it actually operating. is kind of cool. And why won't it show? Your screen sharing is paused. Well, that's gonna fail. And I don't know why. Just look up the um, Falkirk in motion, and you'll see it. So we need to do a new share, and we'll go back to the PowerPoint. Sorry that didn't work. And there we are. It just there's kind of there's a aqueduct up here, and so this thing just rotates. You know, a boat comes along and fills up with water, and it carries it to the top while this one rotates to the bottom. It's pretty interesting. Sorry I couldn't show it to you. Okay, let's continue with Archimedes' principle. Denser fluids will exert a greater buoyant force on a body than less dense fluids of the same volume. A ship floats higher in salt water than in fresh water. Salt water has a density of 1.03 grams per cubic centimeter. Fresh water is 1 gram per cubic centimeter. If we do that in kilograms per cubic meter, that's salt water is 1,030 grams per cubic meter, and fresh water is 1,000 grams per cubic meter. Okay. Now, Archimedes' principle applies to air also. The more air an object displaces, the greater the buoyant force on it. If an object displaces its weight, it hovers at a constant altitude. If an object displaces less air, it descends. So, and you regulate that with, you know, a hot air balloon. You know, you fill it more with the hot air, and it becomes bigger, and you rise. I think it just passed. I think it's every October. The Albuquerque, New Mexico, where my son lives, has a big balloon fest. Okay. As you sit in class, is there a buoyant force acting on you? No, is evidenced by an absence of lift, or yes, due to the displacement of air. Well, you do displace air, so there is a buoyant force on you from the air. However, the magnitude is much less than your weight, so you don't feel it, but there is a buoyant force on it. Okay, and that's the end of part 4, and we'll end it right here. And there is going to be a part 5.